So this lesson is an introduction to acids specifically, but I wanted to go over a couple of things just to make sure that we're on the same page. So first of all, I normally have an entire lesson that goes over pH, pOH, and then your Bronsted-Lowry acids and bases. But you guys went out over that over the summer. So I'm you guys need to take the time right now, pause this video, go back to your summer workbook and look over page 59 to 62. That has all of the information about pH, pOH, and Bronsted-Lowry acids and bases. Because from now on, I'm going to assume that you've mastered that content. Okay, so pause this video, go back and look over those pages. Now, what I'm going to talk about is strong acids and strong bases. I'll actually show you how to determine if an acid or a base is strong. However, first of all, there's going to be a list of 6 acids and then some bases that are strong that you have to memorize. And this is going to be one of the few times that you actually have a quiz in class at the very beginning of the period. I'm going to just ask you guys to write out all the strong acids, write out all the strong bases, and you'll see why that's important later on in this lesson. So your strong acids are HCl, HBr, HI, HClO4, HNO3, and H2SO4. So I would recommend creating some kind of mnemonic to remember the strong acids, because those are the ones that are slightly difficult to remember. Your strong bases are really easy to remember. They're going to be all of your group 1 metal hydroxides. So for example, sodium hydroxide, lithium hydroxide, etc. So any group 1 metal with hydroxide, and then calcium, strontium, and barium with hydroxide. Those are going to be strong bases. Okay? So in this lesson, we're going to specifically just be working with acids, but I need you to memorize both groups so we don't waste time in class forgetting it. And you'll see in a little bit why we really need to know what's a strong acid and what's a strong base. All right, so for new content, when we're dissociating an acid, and again, I'm going to go through this in even more detail, but I'm going to show you the generic formula for the acid dissociation and then base dissociation so that we can look at 2 new equilibrium constants. So for acid dissociation, you're going to have an acid, HA, and it's going to break apart into its hydrogen ion and some sort of anion, whatever it is. Okay? And again, we'll go into this in more detail in just a couple of minutes. However, what we can do, since this is a form of equilibrium, I can actually write out an equilibrium constant for this reaction. So Ka will be the concentration of H plus times the concentration of A minus all over HA. So that's nothing new. The only reason why it's Ka is because this is an acid dissociation reaction, which begs the question, okay, what if it's not an acid dissociation reaction? What if it's a base dissociation reaction? Well, in a base dissociation reaction, what happens is you've got your base, whatever it is. We're going to show it reacting with water, and the reason why we need to show water is because, remember, bases accept a proton. And if I just said that and you're like, I don't remember that, go back to the summer work. You've got to have that mastered. Okay, bases accept protons, so it's going to steal a proton from the water. So you now have Hb plus, and then it produces hydroxide since that hydrogen was stolen. Okay, so when I write out my Kb, and it's Kb because I'm in equilibrium and it's a base dissociation reaction, I'm going to have the concentration of hydroxide times the concentration of Hb plus all over the concentration of my base. Keep in mind that we exclude water because it is a liquid. All right, so why do we care about these values, about your Ka and your Kb? Remember from before, the larger your K is, right, the larger your Ka or your Kb, the more products are forming. The more products that form, the stronger your acid or your base. If you have a very large Ka or a very large Kb, that means that that acid or that base is being able to dissociate really well. It's being able to break up into these ions, making it either a strong acid or a strong base. So the larger your Ka or the larger your Kb, the stronger the acid or the base accordingly. So let's talk about one last concept with acids for right now, and that's polyprotic acids. So a polyprotic acid is an acid that has more than one hydrogen that it can lose. So as an example, you've got sulfuric acid here. So remember, sulfuric acid is one of your strong acids, H2SO4. It will dissociate. Remember, it's going to lose one hydrogen ion at a time. So it will break apart to form hydrogen ions and HSO4 minus. Now notice HSO4 minus still has a hydrogen. So it can act like an acid and it can donate a hydrogen ion to become H plus and SO4 2 minus. So this is a polyprotic acid because it can lose more than one hydrogen ion. One thing that I want you to note, look at the Ka values. Okay? The Ka1, which means for the first hydrogen that is lost, the Ka value is 100, while the Ka2 for losing the second hydrogen is 1.2 times 10 to the negative second, so it's a lot smaller. Well, why would that be? If you notice, HSO4 has a negative charge. If it's already lost a hydrogen, its negative charge is going to hold on to that second hydrogen much more tightly than H2SO4 will because it has a neutral charge. So since HSO4 minus is holding on to that hydrogen ion much more strongly, the Ka value is going to be much lower. It's going to be a weaker acid because less of it is going to be able to break apart into H plus and SO4 2 minus. So since it's harder to remove the H plus, the harder it is to remove the H plus, the weaker your acid, because remember, a strong acid, it's able to break up into its ions. So let's look at some other polyprotic acids really quickly. You see sulfuric acid there. It has 3 hydrogens to lose, so it's going to have 3 Ka values. Notice how progressively they get much smaller. It goes from 7.5 times 10 to the negative third to 6.2 times 10 to the negative 8th, all the way to 4.8 times 10 to the negative 13th. So the more negative that acid becomes, right? Because after Ka1, it's H2PO4 minus. After the second one, it's HPO4 2 minus. So it gets harder and harder to remove a hydrogen. The harder it is to remove a hydrogen, the weaker an acid is. All right, so there are some other polyprotic acids just for you to be able to look at. All right, so last concept really quickly. I talked about Ka and Kb. Remember, Ka is the equilibrium constant for an acid dissociation. Kb is for a base dissociation reaction. And we can actually compare the two. And if I'm given Kb for an acid dissociation, I can actually really easily calculate the Ka value. And the way we do that is we know that Ka times Kb equals our Kw, okay? Kw comes from the equilibrium reaction for the autoionization of water. So the fact that water actually can act as an acid and a base. And so at 25 degrees Celsius, your Kw will be 1.0 times 10 to the negative 14th. Keep in mind, all bets are off if you're not at 25 degrees Celsius, and we'll talk about that. But if we're at 25 degrees Celsius, since we know our Kw, if we know our Ka, we can figure out our Kb. And if we know our Kb, we can figure out our Ka.
Okay, so let's actually look at the dissociation of a strong acid. So when a strong acid dissociates, we don't actually need to use an ice chart because all of our acid is going to dissociate, but let's actually look at it and see how the ice charts work because it still works with ice charts. So here I've got perchloric acid and it's going to dissociate completely into its ions. It's going to dissociate into hydrogen ions and perchlorate ions. And so I'm going to create an ice chart. Okay. And the problem tells me that I start with 0.040 molar of my strong acid, and I don't have any of my hydrogen ions or my perchlorate ions. So the change that's going to occur is going to be minus 0.040 for perchloric acid. Now the reason why is because, well, based on the definition of a strong acid, 100% of it is going to dissociate. And therefore, I already know my X. It's negative 0.040. So it's going to be plus 0.040 and plus 0.040. And so at equilibrium, I have none of my perchloric acid, and I got 0.040 of my hydrogen ions and 0.040 of my perchlorate ions. So what I can do to calculate my pH, it's actually quite easy because right now I already know my concentration of hydrogen ions at equilibrium. It's 0.040. And so what I can do is just take the negative log of 0.040 and that will give me my pH. So my pH equals 1.40. And the reason why it's the 0.40, remember, 2 sig figs gives me 2 decimal places for pH. So that's for strong acids. Same thing for bases, except it would dissociate into hydroxide ions and then the metal ion, and you'd simply take the concentration of your hydroxide ions at equilibrium to find POH and then pH. So really not bad. Let's look at weak acids, because for weak acids, you have the complication that not all of the acid is going to dissociate. So there are two different ways of writing a weak acid dissociation. The first one, notice I've got HA, my acid, and it's going to be dissolved in water, and it's going to form hydronium ions, and then your other anion. Now, that's one way to write it, because remember, for an acid, it donates a proton. Or the other way, which I prefer to write it, is simply your acid dissociating into its ions, like what we did for the strong acid in the previous slide. We will interchange the term hydrogen ion and hydronium ion because notice, other than the water, which we'll ignore for ice charts, those are the exact same reactions except for the fact that you have hydronium in the top one and hydrogen ions in the bottom. So I tend to use the bottom one. Either one is perfectly fine. Let's look at an example. We are going to calculate the acid dissociation constant, your Ka, when you're given pH. So in this example, it tells me that I have my acid. So I'm going to write out my reaction right away. I've got my acid dissociating into hydrogen ions and then that anion. So I'm going to create my ice chart like before. My starting concentration is 0.10 molar, so I'm going to put that there, and I don't have any hydrogen ions and I don't have any of that anion. And so the change that I'm going to see now, instead of being able to just say minus 0.10, I can't because this is a weak acid. So I've got to subtract x, add x, and add x. And so what I end up getting at equilibrium is 0.10 minus x, x, and x. So normally the next step that I would take would be to write my equilibrium expression and therefore calculate my acid dissociation constant, or my Ka. However, here's one important point. Notice this problem gives me my pH. It tells me that my pH equals 2.38. So what I can actually do first is take 10 and raise it to the negative 2.38 and calculate my concentration of hydrogen ions. And what I end up getting for that is 0.0042. Now I wrote x equals 0.0042 because that is your concentration of hydrogen ions. And so now I know my concentration of hydrogen ions, I know my concentration of my anion, and now I know I can figure out by subtracting the concentration of my acid. And so I'm going to plug that into my equilibrium expression to calculate my Ka. So my Ka equals my concentration of my hydrogen ions times my concentration of my anion all over the concentration of the acid. So now I know my Ka equals, well, the 0.0042 times 0.0042 divided by the concentration of the acid, which by subtracting I find is 0.0958. And so my Ka for this is going to be 0.0018. And that's it. Now, instead of solving for Ka when I'm given pH, what if I need to calculate the pH when I'm given my Ka? Let's look at an example. Here it gives me acetic acid, and it gives me my Ka and asks for the pH. So I'm going to first write the acid dissociation reaction. So I've got my acid dissociating into my hydrogen ions and my acetate ions. I'm going to ice it. I know the initial concentration, 0.30, and then 0 for hydrogen ions and 0 for acetate. It's going to change by negative x, so minus x and then plus x, because again, this is not a strong acid. And so at equilibrium, the concentrations will be 0.30 minus x, x, and x. Okay. Now what I need to do is I need to write my equilibrium expression. And so I know my Ka here is 1.8 times 10 to the negative fifth, so I'm just going to plug that in. And that's going to equal my concentration of hydrogen ions times my concentration of acetate ions all over my acetic acid concentration. So now I can plug in my variable. So 1.8 times 10 to the negative fifth equals x squared over 0.10 minus x. Okay? Now, here's the thing. Based on the rule of 100, if you take 0.30 and divide it by 1.8 times 10 to the negative fifth, that's going to be greater than 100. Therefore, I can ignore the minus x right there, and I can easily solve for x now by multiplying 1.8 times 10 to the negative fifth by 0.10, and then taking the square root of that. And so I get x equals 0.0013. Now, you might be tempted to want to be done at this point. However, notice that's just my concentration of hydrogen ions, not my pH. So to find pH, what you need to do is take the negative log of 0.0013, and what you get is 2.87 for your pH.